रुको यार. Hello. Okay. We're almost ready. Please give us a couple of minutes. Hello. Good morning, everyone present here. It's a great pleasure to warmly welcome all of our participants, attendees, students, scientists, staff members, and esteemed colleagues. More importantly, the students from Balchandra Group of Institutions to this special session organized as a part of the year-long celebrations marking the 75th anniversary of the establishment of CSIR-CDRI. The Innovation is Healthcare Oration is a visionary initiative spearheaded by our director, Dr. Radha Rangarajan. This series aims to bring together distinguished researchers with outstanding scientific achievements, providing a platform to inspire new ideas, foster innovation, and encourage transformative thinking in the healthcare. In the past editions, we were privileged to hear the outstanding talks by Dr. Dibabrata Sengupta, Dr. Bushra Atik, Dr. Samrat Mukhopadhyay, Dr. Dibabrata Maiti, and this year, Dr. Arvind Bansal. Today, we proceed with the second lecture of this year's Innovation in Health series of oration. It's our honor and privilege to welcome today's esteemed speaker, Professor Raghavan B. Sunoj from Indian Institute of Technology, Bombay, Mumbai. So, I now invite the dignitaries to the dais, Professor Raghavan B. Sunoj, Dr. Radha Rangarajan, and Dr. Prem Prakash Yadav. May I request the Director, CSIR-CDRI, to formally welcome Professor Raghavan Sunoj by presenting a bouquet. I now invite the Director for her welcome address.
Good morning, everyone here, faculty, staff, CDRI students, students from the Balachandar group, and of course, Professor Sunoj. We are gathered here for the last talk in the Innovation in Healthcare series for 2025. As Arvind mentioned, this talk series is held once a quarter, and we bring distinguished scientists to CDRI to talk about their research, particularly in the context of therapeutic applications. We are deeply honored that Professor Raghavan Sunoj from IIT Bombay accepted our invitation to be here today. Thank you so much for making the trip out. It was actually scheduled for earlier in December, but Indigo Airlines had other plans for us. So we are here at the very end of 2025. I know many of our colleagues are not here because they are taking an annual break. I think they will miss out on a fabulous talk today. Maybe we will get you to come one more time in the near future. I understand this is Professor Sunoj's first visit to CDRI, and hopefully there'll be many more. Professor Sunoj's current research interests lie at the intersection of chemistry and AI. In particular, he's using machine learning and generative AI to predict chemical reactions, that is, outcomes, yields, enantiomer selectivity, and so on. As you can imagine, this has far-reaching implications for basic and industrial research. It opens up the possibility of exploring synthetic methods with greater precision and higher chance of success. And applied to drug discovery, such methods could unlock the potential of new chemical scaffolds that are currently considered difficult to pursue or considered too risky. His research has been recognized widely, and he is a recipient of the Bhatnagar Award for his scholarship and research. Beyond his academic interests, Professor Sunoj is a much-loved teacher. He is known for his engaging style and his dedication to students. I had the privilege of listening to him at IIT Bombay a few months ago, and I can tell you that Professor Sunoj has a gift for being able to explain complex ideas in simple terms. No doubt this is what makes him popular with his students. I also read that he occasionally shows up in the hostels before the exam and does personal tutorials with students who are, perhaps feeling a little nervous about the exam. This kind of dedication is really incredible, and he's been recognized for his teaching capabilities as well. So we are in for a treat today. I look forward to the talk. Before I hand the stage back to Arvind, I'd like to thank the committee members, Dr. Prem Prakash Yadav, who chairs the committee, Neeti Kumar, Jia Gayan, and Arvind Chatri for making this event happen. I think this is the last talk this is the last event that this committee will organize through the year. They have put in significant time and effort into ensuring that we have high quality talks. So thank you once again, and thank you, Prem, for your special effort in bringing Professor Sunoj here. Thanks to everyone in the audience, and I look forward to today's talk.
Thank you, ma'am. So I will give a brief introduction. So Director has covered most of the expertise of Professor Sunoj. I have some more points to add. So Professor Sunoj is from Department of Chemistry, IIT Bombay. He obtained his MSc with first rank from University of Kerala and his PhD in chemistry from IISc Bangalore. He began his scientific journey as a postdoctoral researcher at the Ohio State University, and he subsequently joined IIT Bombay, where he rose through the ranks from assistant professor to full professor in 2012. Professor Sunoj is a distinguished scientist with over 182 publications, more than 8,800 citations, and an H index of 54. He is internationally recognized for advancing modern chemistry through AI. His numerous honors include the National Award to Teachers in 2023, Shanti Swarup Bhatnagar Prize in Chemical Sciences 2019, Fellow of Royal Society of Chemistry London, and Fellow of National Academy of Sciences India, among many other prestigious accolades. He currently serves as Associate Editor of Journal of Organic Chemistry, ACS, and holds advisory positions on leading editorial boards including Chemical Science, Chemistry Journal of Computational Chemistry, and Organic Letters, shaping global scientific discourse in theoretical and computational chemistry. His pioneering research integrates molecular machine learning, generative AI, and reinforcement learning to solve one of the chemistry's more profound challenges: predicting reaction outcomes, yield and enantiomer selectivity, and guiding real-world asymmetric catalysis with reliable synthesis pathways. Today, we are privileged to hear his insights on molecular machine learning and generative AI for chemical reactions. So please join me in welcoming Professor Sunoj for his talk.
Thank you so much for the invitation and very profound introduction. Whosoever said it, I'm very honored to be here. It's a great institute I've been hearing from my earliest of academic journey as a master's student, or when you try to enroll for PhD, looking at various institutions and the kind of work that this country can offer where you can be part of. CDRI has been a prominent institute of recognition youngsters look up to, and I'm really proud to be here and delivering this lecture in this healthcare innovation series. I was in the morning walking around the campus, ably guided by one of your colleagues, Neeti. Thanks for the tour. Really enjoyed the cold weather. Mumbai, it is like 22, 23 degrees Celsius, and it's much cooler here. I'm enjoying my stay here. Had nice aloo paratha in the morning. Very, very warm, and hospitality is wonderful. And Prem has been so kind, following me from point to point. Have you reached? Where are you now? When are you coming? So it was very, very kind of him, and I really feel, the warmth of people here, and very happy that I got this opportunity to talk to you people. Let me begin with my insistence that I want to come in person as opposed to an opportunity extended to me. That Indigo story was mentioned. So after the Indigo story, I was given this chance that, why don't you give a talk online? I said, after teaching 3 semesters online, I've taken a pledge in life that I won't go once more online. Okay, so hence I'm here. I flew into Lucknow yesterday. Very impressed with the city and what the city can offer. Nice roads compared to Mumbai traffic. So it is a very, very good experience so far, and I look forward to interacting with many of you. The whole purpose of coming down in person was to establish human-to-human contact in the world of AI. Things are getting so virtual, so uncharacteristically unreal, that I want to see people. I want to talk to them. I want to have eye-to-eye contact. And I was telling Prem that what would be the lecture content would be. I said, my content remains the same, but the way I deliver depends on how audience respond. So if you get connected with the content, then I will be more energized. I will be spending more energy trying to convince you that, oh, it's great. But on the other hand, since you are honoring off-par principle here, what is off-par principle? Lower energy orbitals get occupied first, followed by higher energy orbital. But that seems to be not true here. That highest lying orbitals are filled first, followed by lower lying orbitals. So there are several empty seats here. So I will try to live up to the expectation, and those who wish to doze off in the morning on a cold day, I'm okay with that. I will try to wake you up nevertheless. So with that said, let me talk about some of our research activities. I would try to make it least boring. Of course, there will be some component of boredom associated with any scientific talk, which I have realized myself. I was on a Gordon conference and a reaction mechanism conference 2 times in the peak of jet lag, just arrived the previous day, and having to listen talk on the following day. I could not recover from the sleep deprivation. And I was sitting next to my postdoctoral advisor, and talk started. Within 30 minutes, I was deep into sleep. Then I realized that lectures can induce sleep more than when you want to sleep. So with that said, if you go to sleep, I will try to wake you up, but I won't mind, okay? So what are we going to talk about today? And as an institute of prominence like this, everyone knows that structure, property, reactions are 3 cornerstones when you talk about the molecular world. There are molecules with exotic properties, and only that molecule can deliver such attributes. And some molecules would be extremely soluble in water. For example, sodium chloride. Earliest of experiment that one can remember is household experiment of trying to learn what is saturated solution. You keep on adding, and when you have a throat pain, you want to gargle, so you keep on making a saturated solution. These are acquired knowledge. No teacher needs to teach you, or you may have to study. But structure property reactions are 3 major cornerstones of how we survive and how long we can survive. We should have good clarity on how would structure impact property. And I will distill down structure one step further. Structure simply means connectivity. And those who are scared of stereochemistry, don't worry about it. I'm not going to present much of stereochemistry today. R configuration, S configuration, EZ isomers, and conformational differences, etc. It's not part of today's talk. But you can imagine, structure to me is just primary connectivity. Primary connectivity. A carbon is connected to next carbon is connected to next carbon, very next atom is a hydrogen, very next atom is an oxygen, next is a nitrogen, then carbon, carbon, carbon. Seems like a boring sequence of linear way of talking about what is a molecule. I'm just implying primary connectivity. Where is primary connectivity elsewhere? It is the amino acid residues through peptide linkage connecting to form a small peptide, and large number of peptides together forming an enzyme-like gigantic structure. Again, boils down to primary connectivity. So to me, connection between atom is the first building block of structure. So I would be using that in the talk today. Second, if H is connected to oxygen followed by one more H, and we call it water, right? And we also know the geometry of water, having a bend structure and so on. And it has so many properties associated with water because of the electronegative oxygen at the center. And if you think of water, let me try to embellish this idea of how properties can be dramatically different when compared to its building blocks. Think of hydrogen. Hydrogen is a fuel. Hydrogen will not burn and produce energy without support from oxygen. Hydrogen combines with oxygen to form water. Oxygen as such will not burn. Hydrogen burns, but not in the absence of oxygen. Hydrogen burns in the presence of oxygen. Oxygen as such cannot burn. And they produce flame, and almost invisible flame, hydrogen burning. And then they produce water, and water would put out the fire. Look at the contrast. When you look at property, property of H2 as a fuel. Property of oxygen does not contain any fuel element, but it supports burning, supports fire. But the daughter that is formed out of H2 and O2 has no property in common with respect to O2 or H2. Wonderful, right? Just sequence OOHH is now HOH. The connectivity is different, property is entirely different, and water has universal solubility and whatnot. I can go on elaborating this. In the interest of general audience and diverse audience present here, I'm just saying that primary connectivity is very important. I'm sure that is well-laid foundation. Then there are compounds which are extremely polar, compounds which are highly lipophilic. You think of this hydrocarbon network. You have octanes and dodecanes and so on. They can also form like from gaseous state to liquid, then eventually to solid. They can pack. And then when you look at a hydrocarbon, long alkyl chain, hydrophobic alkyl chain, there is no functional group. So when you talk about property of an alkyl chain, long alkyl chain, it is lipophilic and it is hydrophobic. These are again properties, but mandated by the primary connectivity of CH2, 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 CH2. An echo of CH2, unending long sequence of CH2 makes it oil-like. Gasoline, diesel, and all that, long alkyl chain. Again, connectivity to property. The property such as its ability to burn in oxygen, produce energy, and that will power a automotive, a train or an automobile or a ship or whatnot. It comes from the conversion of carbon to CO2 and water, right? So we are having a glimpse of primary connectivity, structure, property, and its reaction delivering energy. Is very common that these sort of things are foundational to the knowledge and to the understanding of chemistry. Let me bring a very interesting molecule. I have no particular personal interest with any of these molecules. Chemists are usually obsessed with their compounds of interest. I'm not very much obsessed with any compounds because I don't touch them, I don't inhale them, and I don't handle them, for which I am blamed, but that's a different story. So this compound, azulene, an exotic species, if you talk about connectivity, it's an aromatic compound containing CH units, CH building blocks. All around there is double bond and so on. That is to do with the structure. Then as far as property, deep blue color, and it has a pepper smell. One more embellishment to the property. So there is a color, there is a olfactory reflex that this compound would induce. So this is how one can perceive structure property. Just an example to tell structure property is inherently interesting. But how about reaction? In reaction, you don't necessarily have one unimolecular dissociation of a, let us say, a xanthate ester. If you heat it to high temperature, it will break down into compounds of interest. Unimolecular dissociation. There are many unimolecular reactions, but those are very small subset of chemical reactions. But often, chemical reactions will involve multiple molecules coming together. Multiple molecules coming together, and there are so much happening in a chemical reactions. There is energy, there is collision, there is collisional frequency, temperature would matter, solvent would matter, viscosity of solution would matter. There are numerous factors which would influence outcome of a chemical reaction. And those who work at the bench would have a regretful memory from their own experience. Yeah, so many things would matter. Had I known this, I would have earned my PhD 3 years before. So many factors matters to chemical reaction outcome. Had I known this, I would have done it better. But my point is, there is so much knowledge out there. So many chemical reactions already reported in literature. Let us say authentic chemical reactions reported in literature. We, as a community, is underutilizing what is out there already. That's my submission. Point number one. That can we make better use of known chemistry so that we can predict ahead of experiments that if you were to try this reaction with this, say, compound A, if you were to try this reaction, would I get desired product? Would I get desired product in decent to good yield? Would I get a product at all? So if you have known this, you are better prepared. At least you are emotionally better prepared. No point doing that reaction because AI predicted it won't work. So I'm slowly slowly building in potential intervention from this massive gigantic monster called AI in the chemical space. So I talked about structure property, talked about reaction, then I'm talking about what is already out there in the form of known reactions. So I want to learn from known reaction, not as a human, but train algorithms to learn from known reaction. Does it make sense? Known reaction. So I'm not discovering any reaction, okay? Known reaction. If I can learn more about chemical reaction, such as experimental methods, you can look at reaction mechanism, you can look at rate of reactions, you may want to look at intermediates formed in a reaction. Many intermediates have revolutionized the way we practice chemistry itself. N-heterocyclic carbenes, good example, carbocation, each of these are almost winning a Nobel Prize. NHC not yet, but then carbocation, George Euler and many others won Nobel Prize for their discoveries of reactive intermediates. So these are all important aspects when you talk about chemical reaction, where molecules combine, they form different loops of mechanistic steps. One can observe them, one can carry out different control experiments. It's kind of very tedious to collect all this data on chemical reactions. So what are the alternatives available to study chemical reaction? One can look at your, I'm sure many of you would, given an option, would run away from this auditorium if you were asked to read what is this. This is a wave function, okay? And the scary old memories coming back, gushing in, right? Wave function. And this is a time-independent Schrodinger equation. Schrodinger equation is the one which perhaps made you an organic chemist, because you didn't want to deal with Schrodinger equation, so decided to do organic chemistry. Okay, so Schrodinger equation can offer very good insights about molecule, great insights about molecule. Good thing about Schrodinger equation is that if you can solve h of psi equal to E psi, that equation, however stupid it may be, but however great it may be, if you have solved Schrodinger equation and you have wave function, the good thing about that, you know everything about that system. If it turns out to be that a Schrodinger equation solved for water, you know all property of water known in the past, known as of today, and would be known tomorrow. Okay, so if you know Schrodinger equation, solved Schrodinger equation for water, that same wave function is useful for all known properties of the past, all properties of interest today, and all properties which is yet to be discovered tomorrow. It's time invariant. That's the power of Schrodinger equation. So we apply Schrodinger equation to molecules, reactive intermediates, catalyst, catalytic cycle, whole bunch of other things. I will not burden you with any of those, but our interest in our research group is to look at reaction mechanism, understand the origin of stereoselectivity, and use non-covalent interaction to engage in design of new catalyst. This is a line of work which we do, and today's topic is not to do with any of my conventional research, but I would be talking mostly about how machine learning can be used for studying chemical reactions and perhaps to guide new reactions, new directions in chemical reaction discovery. Just one slide which I am tempted to show, because this has been our activity. No intent to show the papers at the lower part of the slide, but to say that there are many non-covalent interactions which we were harnessing in our laboratory to understand reaction outcome, because this will have implications later in my interest in integrating non-covalent interactions into the AI subspace, where if you want to work in catalysis, conventional homogeneous catalysis for instance, and large part of enzymatic catalysis, it has to do with subtle changes with one preferred path versus another less preferred path. Subtle changes. The re-prochiral phase versus alternative psi-prochiral phase, the difference is less than a few kilocalories per mole. When you talk about two competing options, competing pathways leading to different stereoisomers or different products, if the difference is small, what would be the immediate readout? If the difference in energy is small, the structures, the transition states or the energetics are almost very, very similar. So the origin of such small differences has to come from subtle changes in the kind of interactions what I have enlisted here. So these interactions are very vital in chemical reaction outcome. These interactions are very vital in several biological processes such as hydrogen bonding, CH pi and whatnot. So we have done a lot of work in this front using electronic structure applications, that is solving Schrodinger equations for transition states, chemical reactions and so on. Now today's talk would be on working with small data sets collected from known reactions and with an intent to predict the outcome of such reactions, outcomes such as yield of reaction, for instance. So we developed machine learning model for real life reactions. None of our reactions are unrealistic because they are all well founded in current literature, literature spanning about 10 to 20 years in recent past. And then we harness this power of generative AI to generate new candidates, which could be new substrate and which could be driven by a particular target that you want to make. You can do a disconnection approach and you can decide what reaction, forward reaction you want to do to accomplish that sort of targets. That's one line of use of generative AI. Now, before I go further, two important things: that can AI solve every problem in the world, particularly in the world of molecules? Not at all. Not at all. I'm being just realistic and brutally honest here, because AI models depend on something called no free lunch theorem. That means your training data is starving. You're making the model starve without having sufficient number of training data. Your model is going to miserably fail. That's what is the implication of no free lunch theorem, that you can make a very good property prediction data set, which is very relevant to CDRI's mandate. That suppose you are interested in log P prediction, which is very important attribute of a molecule which could potentially be a drug candidate. If you want a log P prediction model and you have a set of compounds which are well behaved and you have the, let us say, experimentally known log P values, and your data set is fewer and sparse. Sparse means, suppose we have a scale in log P, let us say 0 to 10 for argument's sake, and most of the compounds in the training data set are between 7 to 10, and one compound at 5, two compounds near about 0. So can you imagine a sparse distribution? One or two candidate near 0, one candidate in 5, rest of the candidates near close to 8 and above. This is an imbalanced distribution. So if you were to make a machine learning model to predict log P with such training data set, the outcome would be that the model will do well as long as a candidate has values closer to 10. But it would miserably fail when the value is around 3, real value is around 3, model will predict it as 9. So there is no free lunch theorem. Second thing, if we are unaware of the data set and its quality or its source and how reliable it is, you are basically putting this data set into a machine learning model to train it, and this is almost like garbage in, garbage out. Garbage in, garbage out would mean that you put poor quality data into the training phase and you are going to get some random performance number, but it will not live up to the expectation when you actually deploy it for real life application. That's where we differ in terms of making our research grounded. Grounded means it is directly connected to experimental realities. We don't fool the model, neither we don't fool our readers. So with this said, let me give a very broad overview of what is this magical machine learning stuff is about. You need a training data. So I may use an analogy that a lot of things in our life we acquired knowledge by mere observation. Okay, so if I pull out a leaf from this plant and show it, can you identify the plant or the tree from where this leaf was plucked? What would be your response? You will say, like Barack Obama used to say, yes, we can, right? You will say, yes, we can. because nobody taught you in the classroom. Did any teacher taught you how to identify a plant based on just looking at the leaf? No one taught. But you acquired that knowledge. You can confidently say, oh, this is a neem tree. This leaf belongs to a neem tree. This leaf belongs to a palm tree. This leaf belongs to a mango tree. You will be very, very confident in saying that. You acquired that knowledge based on observation. So let us now call it an observation as an instance of learning. You saw a plant and you focused on the leaf and you mapped leaf to that plant. That is an instance. You observed and you have kind of acquired that knowledge and you know it. And any future episode where such a leaf is presented to you, you will immediately say, oh, this is that plant. Are you confident? Yes. But how about a leaf which is not seen before? You would still make an effort. Oh, I don't know, I'm not sure. Uncertainty. Yeah, your prediction, your forecast become less certain. But you would make an effort. Oh, it looks like neem tree. Looks like neem tree, but I'm not sure, right? So model has its own uncertainty. So imagine a model training with garbage data set. The model is as good as garbage only. So this is where domain expertise become very important. That if you want to develop machine learning model for molecular space, such as property prediction task or reaction outcome prediction task, it is better to always have a domain expert in the loop, with who can never be replaced. That's the reality. More of AI, more I am getting convinced that it is domain expert at the center of the AI model would deliver. And if there is a vacuum instead of a domain expert, AI can create disasters which are yet to be proven, and it is in the making. So with that said, so we will have several such instances to train the machine learning model, and you can predict property. And there are two aspects here. One is called a training phase, and other is called an inference stage, or the test time. Test time means you send a new sample to the model, that means a new candidate to the model, and it will give you log P within microsecond time gap. You send hundreds of new compounds to this model, within 30 seconds you get log P predicted by the model in about 30 seconds. Very fast. Inference is usually very fast. So this is the standard setting of machine learning. You train the model with good quality data set, then it is all set to predict on unseen scenarios. So in the molecular world, there are different options, different opportunities to represent the molecule, so that the algorithm will be able to understand what is the primary connectivity. For example, if you look at this molecule, acetaminophen, if you look at the primary connectivity, this is the sequence in which the molecules are fed into the model, what we call as input to the model. The input would be represented in a linear array of strings, which are which has its own meaning. The capital carbon, small carbon, which is part of aromatic system, and oxygen, nitrogen, the primary connectivity. This is called a Smiles representation of molecule. Alternatively, you can train your machine learning model by using molecular graphs, which is a very well developed area in computer science. A graph, it comes originally from mathematics, but computer scientists have made use of graph-like representation for social media forecasting, recommendation systems, identifying friends who would potentially be of interest to you, and products that if you search something on Amazon, you will get this recommendation. Customers also viewed or bought, so you get recommendation. A lot of those backbone works in graphs, and something which is most practical day-to-day use is traffic prediction. Traffic prediction, the backbone machine learning model is graph-based model. Okay, for traffic prediction, this may be an intersection, this may be a merging road, and this may be a highway, and so on. So this is universally applicable. The graph is very powerful. One can use Smiles, this molecular fingerprint. This is also very popular in pharma industry, fingerprint-based representation, or one can use interpretable physical organic descriptors, which would of course require some electronic structure computations. So these are different modes, and not limited to primary modes of defining a molecule in a data set for building a machine learning model. So this will help us appreciate our efforts in reaction outcome prediction. So as I mentioned earlier, reaction involves participation from multiple species. It's not like A transforming to product. It is A reacting with B in the presence of C, in the presence of solvent D. A, B, C, D, all are required to be able to see the product at the right side of the arrow. So the reaction becomes a very composite representation. But then if you leave it to the complexity, that reactions are too complex, so let us not apply machine learning to reaction space. That is one way of taking a back seat and relaxing. Alternatively, you can think that, okay, let me come up with a set of hypotheses. The first hypothesis is that it is the reactant that converts to product. It is, let's say, reactant A that contains reactant, most atoms of reactant A is retained in product P. So therefore, reactant is supreme in any model. That is a hypothesis. Reactant may be there, but I said H2 is a reactant in water formation, but H2 plus O2, without the kinetic barrier, it will stay for millions of years, no water will be formed. So H2 is primary. So define your reactant properly, reactant sufficiently. So that is first hypothesis, that can we think of reaction outcome prediction model building as a simplified problem, notwithstanding the complexity of chemical reaction as having too many components coming together, colliding together. We would simplify this hypothesis by saying that it is the reactant that matters the most. Then you refine the hypothesis. You would say, you would use the plural, it is all reactants that matters to reaction outcome. These are easy to understand hypotheses. Now, if there is a catalyzed reaction, I would argue that it is the reactant and catalyst which matter to the outcome of the reaction. So if this sort of hypothesis can be thought about, then we represent using the standard representations of molecule to predict the outcome. So it is a bunch of catalysts industrially used for a reaction known as asymmetric hydrogenation, very popular set of catalysts. This will work in tandem with a transition metal to hydrogenate compounds shown here. It's a double bond, either as part of an imine or an alkene. So hydrogen gets added across this double bond. That is why it is called a hydrogenation reaction. H2 will split across this double bond, and you create a new chiral center either here at 12 carbon, 16th carbon, or 12 carbon here. When hydrogen is added, it becomes a stereogenic center, and you're talking about enantioselective transformation. That is why you have this axially chiral catalyst used for asymmetric hydrogenation and industrially practiced chemistry. Now, so what we have done, I said we stay grounded and we collect reactions from literature, from published literature. About 400 different reactions were collected belonging to 5 different catalyst families, and amines and alkene together about 190 candidates and 58 catalysts. So total of less than 400 reactions is all we have for training the model. And what we intend to predict is what would be the enantioselectivity in terms of percentage E of this reaction. That's the outcome of this reaction. So this is a label problem. It's a regression problem. That means the value of your output label can be from anywhere between 0 all the way to 99.99. It's your range of values that you wish to predict using your machine learning model. We developed multiple machine learning models for this purpose, and how the model was built by carefully thinking about what would matter to the outcome of the reaction. First, by hypothesizing that the catalyst is supreme, substrate is supreme. If you know the catalyst and substrate and you well represent both of them, perhaps you will find a mapping, a complex high-dimensional mapping that will help you predict what would be the E of the reaction. So for that, we collected molecular descriptors of the kind which is shown here, and global descriptors which are not specific to a region of the catalyst, and then we developed machine learning model. And this is just a summary of this. Some crazy numbers like 8.4, What does it mean? So I will convert them into a number kind of thing. So 92 to 93 predictions out of 100 predictions are within the ground truth, that is actual experimentally reported ground truth enantiomer selectivity for this class of reaction. That means what would be the advantage for this is that suppose I have a new alkene which is a potential precursor to a drug or nth step in a multi-step synthesis where you are installing a stereogenic center using this asymmetric hydrogenation as a key step. In such scenarios, your candidate is new. Yeah, you have this different R1, R12, this kind of substitution. All you want to do is to use an organocatalyzed, this is chiral phosphoric acid, organocatalyzed asymmetric hydrogenation of your double bond. This is what your intent is. Now, and this double bonded compound turns out to be so precious that it took 14 steps to get there, and then you want to do a reduction. Train the model. You're only subjecting the model for inference because it's a pre-trained model for alkene and imine asymmetric hydrogenation using axially chiral catalyst. Therefore, this model is suitable for predicting just in few seconds what would be the outcome. So it can be integrated into workflow. Now, second hypothesis which I wish to make, because I want to go to more progressively more complex models. The first model was much simpler. A more complex model is not really a motivation due to the complexity, but it is a motivation driven by the fact that large language models are omnipresent, and each one of you may be using ChatGPT and other generative AI applications in daily life. So language models are very powerful. So we wanted to see how a chemist can be benefited by language model, and I must at the outset make a distinction that the term language model I am using not from a prompting point of view, because I'm not going to ask a language model, oh, I have I want to do an aldol reaction, hey ChatGPT, will you recommend the best way to do aldol reaction? Then I'm shedding my identity as a chemist, and I should perhaps be not so proud of being a chemist if I'm asking ChatGPT how to do this aldol reaction. So I don't do prompt engineering based language model. I just encode the molecule using language like representation. That's what I mean by using language model for chemical reaction outcome prediction. So here I'm saying my second hypothesis is that reactant, solvent, catalyst, all of them can influence reaction outcome. I'm sure you would agree. The first model assumed key substrate and catalyst only would influence the outcome. That was hypothesis. Now I am refining the hypothesis that many of these factors would influence the outcome. And many among the audience would be thinking, what about solvent? What about temperature? Yes. We are including all of that. So the second hypothesis would be more complex. Looking at a reaction like this, very important, Buchwald-Hartwig amination, widely practiced by pharma industry. I'm in talks with one of those multinational giants to develop regression models for Buchwald-Hartwig type of amination reaction. And pharma being pharma, they won't tell what candidates they have, right? They will not tell you, they will not ever disclose their data set to you. So I'm supposed to make publicly available a machine learning model for predicting what would be the yield of such reaction. So if you look at the complexity, there is a catalyst, a critical additive, base, BMS or solvent, temperature, reaction time, and you have these variables. You would make this aminated aryls, very important candidates. So can we predict the yield with decent, reliable accuracy? So that is the time when we started using, 1 second, I usually lose track of time. So how much time I have? Or already used up? Okay, thanks. Phone is kept there. Maybe it is rubbing it on this. I will remove this. So this is called chilling on stage. You're chilling out. Because why I'm reacting the way I'm reacting now is because I'm getting good feedback from the audience. That's called non-verbal communication. That is precisely the reason I am here in person. I'm in person, I can exchange eye contacts, non-verbal communication with many of you, and I have anchors sitting in the audience already. I don't know them. I know Namrata, Kinshuk, and your director, and many others, and my good friend from IAC days, Pratap, Pratap, and so a few in the audience I know, but I discovered many new members of the audience who are responding to my statements, responding to my non-verbal gestures on stage. So I'm enjoying so far. Yeah. So getting back to business. So this is a coupling reaction, Buchwald-Hardwick amination. So how do we deal with this? Given the power of natural language processing, given the power of large language models, so we thought that we should represent a chemical reaction as a linearized array of reactants, catalysts, solvent, and then predict the outcome. Perhaps that may be better. So with that said, if you look at that reaction, there is a ligand from the catalyst, coupling partner 1, coupling partner 2, they are the ones which couple. This guy would couple with this guy in Buchwald-Hardwick amination reaction in the presence of a base. So now I am going to talk about a sentence just to lighten the mood of the audience, that I have come all the way to Lucknow to give a lecture in CDRI. I have come all the way to Lucknow to give a lecture in CDRI. A longish sentence with many words in between. Now, I am training a model, a language model, which will work during training by way of masking and unmasking. The masking would be, I have come to. So I have come to is part of training. All characters are displayed. I have come to, Lucknow is masked. And the sentence continues, unmasked, to give a lecture in CDRI. So effectively, during several rounds of training, model should be able to figure out it should be Lucknow because CDRI is a prompt. CDRI is at the end of the sentence. So long-term dependency would help the model learn that CDRI is located in Lucknow and the verb is come to, so it should be Lucknow. So during training, it learns it should be Lucknow and it would assign a probability. The word Lucknow is more likely to be present with top K probability. The word Lucknow gets as higher probable word when I use several such sentences describing my visit to this institute today. If I give a passage for training, many words will be learned by the model. Now come back to this. So if I train a model to predict the yield of this reaction, if I were to use these substrates and catalysts, the yield is 90%. And then I mask this and I bring in a new substrate after training. New substrate, if I bring after training, I have a new coupling partner here, rest of the things are same. So it is almost like I have come to Delhi to give a talk at CDRI, wouldn't make sense. So it would learn based on instances, based on prior experiences, which is gathered during training. That is why training is very important. Gigo, garbage in, garbage out. No free lunch. So you should know what you are training your model for and with what you are training the model. That's how it works. So it is data on one hand, model on the other hand. They should mix very well, and the trainer should know the purpose. Yeah. So with that said, this is our long concatenated representation. The technical term is called concatenated representation of your sample. Just one reaction, and which is then mapped onto a value which is yield of the reaction. A very complex outcome of the reaction is yield. And of course, one can debate how do you know that yield is reliable. It depends on the investigator who carried out the reaction. Many things may be stuck in column. There are many other complications, but I should confess that these are engineering solutions to scientific problems. And engineering solutions would always remain approximate in the early days of its invention. Always remain approximate. You don't get a Wright brothers to fly an aircraft from day one. There are many crashes undocumented before you take off from the ground. Yeah. So therefore, these are engineering solutions to scientific problem. There would be numerous errors and approximations as we go along, but one can perfect it when you make further progress. And that's a simplistic mindset that I have, which I learned from my colleagues in computer science, that let's get started. What is known as go get dirty. These are go get dirty days of machine learning. So therefore, no great accuracy promised. unless I want to fool you that, oh, it's an extremely accurate model, then I would be dishonest to myself that after knowing the inner workings of the model, I should not be promising extreme accuracy in my reaction outcome prediction. So this is some inner details of how the model would perceive the input and eventually to predict the yield of the reaction. And how about the performance? So here is what my language-like representation of training with molecular inputs, that it learns connectivity, which I said in the beginning, that it is the primary connectivity that matters the most, which in turn is connected to property, and reaction is one such property exhibited by molecule. So with that, a model can be trained by character level prediction by masking and unmasking, and with the highest probability, given a molecule, it is more likely to be a carbon. In this training, I'm just describing the training in a qualitative sense. It learns to predict next character. That means if there is a benzene in your training sample, the beginning of string will be, let us say, beginning of string, the next character would more likely to be a carbon. Next character again more likely to be a carbon, but during masking, unmasking, training, it learns the probability that if benzene becomes the full closed sample, complete sample, more often you have a chance of seeing a carbon as the next character, which is shown as masked with a question mark. So that is how model learns the connectivity. Once it learns the connectivity, a lot of things can be understood. And here, this is an alternative techniques to deal with small sized data sets, because we don't have too many examples for reaction outcome prediction. Few hundreds and at best 1,000 reactions is what you have. So one can use a transfer learning protocol to train the model for small data sets. So this is just a summary of it. Again, these are well into more than 90 predictions out of 100 are within about 10 units of actual ground truth value for diverse class of reaction. Now I will switch gears, introduce one more small reaction, but here I will connect with or build a bridge with generative AI and give you a realistic picture of what it can give and what it can't. So with that, so this is the reaction. So there is a new stereogenic center that is produced over here. Organic chemists in the audience may be very happy that this is a asymmetric CH activation reaction, asymmetric beta CH activation, beta CH relation to be precise here. And this is a chiral monoprotected amino acid which is used. This sort of chemistry is pioneered by Ching-Kuang Yu in the Scripps Research Institute in California, my colleague Debaprado Maiti in IIT Bombay. So these people have done a lot of work in this beta CH bond activation reaction. So here is the reaction, and number of examples available for us to build a machine learning model is just about 240. Okay, 240. And it comes with loaded sparsity, like this occupation of seats in this auditorium, loaded sparsity that rarely filled, often filled, and densely filled. There are different clusters which you can see by looking around, that friends stay together, like-minded people stay together, people from same lab stay together, those who wear white coats stay together, and so on, right? There are different clusters that are visible here. Now, so we trained a model which contains 77 chiral ligands of this family. And the question is, can we predict the reaction outcome? This is a very busy slide, don't worry about it. I'm trying to tell you that one can develop multiple machine learning models to predict reaction outcome. So we introduced what is known as an ensemble prediction model, whose performance is best because of least overfitting or underfitting. This is a technical issue with machine learning model, that it would make overconfident predictions. So we bypass them by developing large number of models to predict each inference sample. I think I should learn Bharatanatyam or something to deal with this mouse. This has always been technology going back in time. There was simple Logitech mouse which was always good, very precise to point, and so here you see the last block. Yeah, it came back. So ensemble prediction. I wish I had the mouse pad here. The last block, a tiny block which has least overfitting. So we would rely on ensemble prediction. That means every time when you have a new chiral ligand or a new pair of substrates, use this model, predict 30 times using sub-models within the model. That is why it is called an ensemble prediction. And you can take the average of all those predictions as a reliable prediction for this. So how can we prove this? So remember, I told that we have trained language model, that is chemical language model, to predict reaction outcome. And the same language model is now well exposed to chemical connectivity, well exposed to chirality of catalyst, well exposed to reaction outcome for this class of reaction. If so, can we bring that strange leaf from a different garden and show to the model, hey, what would be the outcome of this new leaf? Then it will say, oh, it resembles that leaf, therefore you may get an outcome of this kind. So let's look at it carefully. So here you see this, the blue dots are generated by AI using a technique called latent space sampling. And those who are interested can talk to me outside the lecture. Latent space sampling, and these golden dots are real samples which were in the training data. So let's look at this. The red one in the training data, which had a isopropyl T-butyl group, the model smartly changes a methyl with a hydrogen and says that, oh, I'm proposing this new candidate to be tried in asymmetric beta-CH bond activation reaction. So model makes a very humble contribution here that this candidate may be equally or more effective than known example. So this is where slow inception, slow permeation of generative AI concepts into asymmetric catalysis. And then what we did, we send these reactions. So with substrate this, coupling partner this, ligand generated by AI, no human intervention, generated by AI, and then we send this sample, no outcome known to my experimental collaborator. We send the sample to them, a bunch of 6 samples, 15 samples, and they carry out the experiment. They don't tell us the value, neither we tell them the value, and have a joint online meeting, because I cannot go all the way to California, right? Just to ensure predictions are good. So online meeting, last 2 columns are left empty. So that day morning, my hands will be, inner palm will be sweaty and nervous. How would the values come out to be? And we enter first value, last but 1 column. They enter concurrently their value. Row 2, we enter, they enter their value, we enter our value. Zigzag, zigzag. We enter. At the end of the meeting, you see this prediction versus real. You see this agreement. Near quantitative. It takes a lot of courage to do this, because this is in true spirit of predictive science. Both are masking each other what is the outcome. But we can see that agreement is very good until you come to low E regime. Low E, training samples are so less, error will be large. High E, training samples are sufficient within the small data set. So you have great agreement with the prediction. Imagine real life scenario. What is the utility of this? What if AI can generate bunch of new reactions and you can test them based on the E or yield or whatever parameters of interest to you? So promising candidates can be subjected to test, and in what size AI can do? AI can predict, AI can generate lakhs of compounds in half a day and predict all of them in less than 30 minutes. And then you identify based on your human intuition. That's the last part which I want to emphasize. Oh, it looks really wonderful, really promising. Not yet. That's my response. Oh, really great, really wonderful. AI will take over human jobs and all that fear. Not yet. Many a slip between the cup and the lip. This is the true story. This is there in the paper. Brutally honest, okay? This is there in the paper. How about this? So we send these ligands to them with very promising synthetic accessibility and synthetic complexity score, very, very decent numbers as per literature precedents. Less than 5 is regarded good, less than 4 is even better. And those scores are 2.8, 3.2, this sort of candidates, AI generated. And domain expert looks at it and says, Sunoj, do you really want us to make this? This will be a pain, it will take several steps and many weeks and months. I said no, but I want to record your phrase. Record your first response that we don't want to try this. I want to record that in publication. We don't want to try this. That is the power of domain expert in the loop. So we discarded the first row candidate, although AI gave a confident prediction this would be a good candidate chiral ligand to try for this reaction. We did not do that reaction. And next one, if you look at next row, all that we could see, they approved, they made those chiral ligands. I should emphasize, they made those chiral ligands because they are not pre-existing. They have to make, because this Gen AI, generated new ligands. They made these chiral ligands, and they did the reaction, except to see CO2 bubbling. Nothing else happened. No product. Yeah, being more real. Row 3, everything went great, but no CO2 bubbling, no domain expert discarding the samples. They did the reaction to realize no product formed at all. What is the use of Gen AI? Row 4, all the more successful. Ligand synthesized, showed reactivity, and summarized in previous table, quantitative agreement. So it works, but not always. That's the importance of domain expert. And since I'm running out of time, I would just quickly go through. There are scenarios where you want to maximize the outcome, maximize a property, maximize reaction yield or reaction selectivity. So we have developed reinforcement learning, again with small data sets, to improve the yield of reactions. I would not have time to go into the details. It's a very powerful technique to improve the yield or selectivity of this sort of reactions. And I will show the summary of this. If you look at the distribution here, this would be the last technical slide. The known training data set has a very widespread distribution, average around 40% for this fluorination reaction, the reaction number 1. So alcohol fluorination using sulfonyl fluoride and a base. So the known reactions were about 40% yield for this particular data set. Reinforcement learning could identify new alcohol candidates which could return an average predicted yield, yet to be tested experimentally, average predicted yield much higher than the known example. So this is helping us explore outward using proper reward shaping, explore outward towards more promising candidates by using the power of reinforcement learning. That is what it is supposed to help us with. So we have applied this in the chemical space. And finally, what I have tried to impress upon you is the predictive power of machine learning and its potential for generative applications, but with several words of caution. And my science has always been inspired by experiments with an intent to inspire more experiments. That's my simple working principle. And you would not see usual suspects of funding agencies logos in my slides. Yeah, so I'm making an implied statement here. Yeah. These are people who were incredibly helpful for us to educate us, participate in clearing our foolish doubts, and teaching us their language, that is language of machine learning. They're all from computer science background. 3 of them are in computer science and engineering in our IIT, and this person, Balamurugan, is a computer science PhD from IISc, postdoc in France, and he is in another department in IIT Bombay. They are our active collaborators for our AI effort. And these are the people. I have presented the work of Sukriti and Ajnabu. Sukriti went on to do a postdoc at Cambridge Computer Science Department after her PhD with me, and now looking for a job, actually. Just promoting Sukriti's candidates, perhaps, I don't know. Ajnabiul has done a lot of AI work, reinforcement learning, and now switched to experimental side of AI-driven experiments. So he wants to actually do, wet lab chemistry. So he is in Germany for his postdoc, and these are the current members of the group. And these are the funding the facilities which I extensively use. And finally, thank you all for your patience and kind attention.
Thank you, Professor Sunoj, for his insightful lecture on how machine learning works and how AI can be used to predict the reaction outcomes. That was very outstanding. Now, we hope someday biologists will also able to predict the reactions, how they work, and look into the chemistry part. And then I also really liked you told us that always domain expertise remains superior to the AI and machine learning. That was really gratifying. So now the session is open for discussion. Any questions from the audience? Yes.
Hi, I'm here. Really enjoyed listening to you. Maybe it's a naive question. What if the reactions, so most of the molecules that we take forward for drug discovery, especially in the field of antibiotics, they're very complex molecules. So the examples that you have shown here, they are like one-step, two-step reactions, or they're multi-step reactions?
Maximum 4.
Yeah.
4.
So sometimes the synthesis route is like multi-step, and maybe different catalysts are used at different steps. So do you also calculate the activation energy, the transition state energy to train your models? And if so, what kind of experiments are those?
Yeah, so those are ongoing activities in the group that we are enabling models with energetics, but it's a hard problem taking our own time. But for multi-step reaction, if you have a well-defined target in mind, you can do disconnection approach. There are AI tools available for best disconnection, which will minimize the cost, maximize the forward reaction efficiency. Even Merck is selling a program called Cynthia. Maybe expensive, but there are retrosynthesis, AI-driven retrosynthesis packages available. That may be one way of looking at it. Having said this, if you have a, let's say, 10-step reaction and you're looking at a critical step in the reaction which was bothering, then we could develop customized AI model for that step. You need a diversity of samples though, but it is possible to customize for a given application or what is known as a use case scenario. With transfer learning, we have gone to lower bounds of less than 100. Yeah, transfer learning, but you have to really work hard to make it happen.
For that, we need experiments.
Right. So we use electronic structure method, quantum chemical methods to compute activation barriers. Because if you were to measure activation barrier experimentally, let's say variable temperature, NMR, or some such technique, not all types of reactions are amenable to such measurements. So you will have a data shortage very soon. So you cannot use experimental method.
Sunoj, excellent talk. I really appreciate that. I was wondering, because most of your data depends on already performed experiments. Suppose in the experiments the yields are wrongly reported. So that will be taken in your data set, and how that good for prediction.
Very, very important question. And so I will share a story of we burning our own fingers. So we are developing a model to predict Suzuki coupling reaction outcome. And it turned out that model is doing well, and a few of those predicted samples are outliers, consistently outliers irrespective of whatever machine learning model we built. And then we zoomed into, I asked students to look at what are those outliers, what are they chemically, and they brought me a bunch of this, coupling partners and so on. And then my next question was, where did you get this data from? And then they said, sir, it's from a, I don't know, I can say this, it's from a country. You can guess. Not too far from India. And those are outliers. So anomaly detection is a subspace in AI itself. So one can use, as a precursor, one can use unsupervised learning to find out spurious candidates. In unsupervised learning, you're not exposing the outcome. You're not exposing the yield of the reaction. You're just looking at the patterns in the dataset. So you may be able to spot some strange players using unsupervised learning, finding some members which will not fall in any of these standard clusters and so on. So one can do some remedial measures, but this is potentially a risk. that ill reporting of or claims which are not grounded with reality. That would be an issue. That is almost like fake news. So anomaly detection can be applied in such settings. Thank you.
Okay. Okay. Hello, Professor Sunoj. Like in a multi-component reaction, like where we have reactants, couple of reactants, then solvent, additives, catalyst, and in that case, variation of a very small parameter, maybe temperature or pressure or amount of additive, would result, experimentally, it would result into completely different products, right?
Yeah.
So when you're predicting reaction outcome, which factor predominates? How do you decide that which factor has to be given more importance over which other factor to determine the reaction outcome?
Yeah. Very good question. This is a live problem in the field. How do you deal with activity cliffs? How do you deal with unusual observation? Just by changing a methyl group, you can see dramatic difference. Solvent polarity by 10 units in dielectric can make things very different. So we are not yet there in the activity cliff regime, but there are techniques to accommodate this sort of high sensitivity. There are techniques called attributions. Okay, so you can, for instance, in asymmetric hydrogenation, from the perspective of interpretability of model, whether the model is really learning some chemically meaningful information, it turns out that the carbon-carbon double bond or carbon-nitrogen double bond in the case of imine, that stretching frequency is very important for model to learn any outcome prediction for reaction of amines and double bonds in asymmetric hydrogenation. So model is learning something chemically meaningful. Now your question is that one of my R12 substituent turns out to be some exotic substituents which was never seen in the training. Will the prediction be reliable? My answer is with a pinch of salt. If it is a very spurious candidate which is potentially a activity cliff kind of scenario, model is not reliable. Yeah, but it's an important consideration that people are worried about.
Professor Sunoj, excellent talk. I think it's apparent to us that there is a huge possibility in the world of chemical synthesis if we can really build good models. The way you're going about it is you're picking one particular type of reaction and then building the model. So is your goal to pick such examples of very key or commonly used reactions, named reactions and so on and so forth, build models around them and put them out there? And do you think that in the big picture, I mean, people are interested in multi-step synthesis, for example, the application would be a critical step or something like that? Or do you envision, like a lot of companies are doing now, which is that you say, I want to make this, and it spits out some sort of synthetic process. But these are still very error-ridden. So what is your view of how to solve this problem? Do you think that we should be looking at the entirety of chemical synthetic space, or focusing on named reactions or key reactions, because that is where we have the most data? That's one question. The second question is, how do you decide how to represent your data in the training process? For example, there are language-based representations, there's graphs, there's smiles. How does this impact the accuracy of your model?
Okay. Both very valid, important question. First one is that USPTO dataset is sufficiently diverse, although it has a very large representation of, let's say, decarboxylation or ester hydrolysis and stuff like that, but it contains a repository of diverse reactions, and those reactions are used as a standard benchmark. USPTO, the performance of a newly developed ML model for reaction outcome prediction should be demonstrated on USPTO dataset. It has become the norm. It's like a baseline, you provide a baseline. So our models have been extensively applied to USPTO, and the choice of a given reaction is based on the impact that reaction has produced in the field. It could be a reaction of high contemporary interest, such as beta CH asymmetric annihilation of through beta CH bond activation, and these reactions may flourish and get adapted by industry in future. But currently, it is of academic interest, hence that choice. Whereas asymmetric hydrogenation, day in and day out, industry uses it for reduction. Okay, but am I biased towards a particular class of reaction? My answer is I wish not to be biased, but I have the temptation to address the so-called state-of-the-art reaction class. So my choices would have an implicit human bias towards selection choice. Like, why I want to work on beta CH? Because I may have an able collaborator who can validate our predictions. So there is a human bias. But otherwise, when I look at chemical reaction space, I'm not interested in a particular reaction for any particular reason. For me, it is a representation learning problem. So I'm okay in dealing with any sort of reaction. So now we are developing a huge data sets and transition state prediction on cycloaddition. So why cycloaddition? Because it's well behaved, governed by Woodward-Hoffmann rule and stuff like that. So there's a working principle behind such class of reaction where the human level predictability itself is quite good. Why not train our concepts, build our concepts into relatively better behaved reactions first and then expand outwards? So these are last 7 to 8 years of effort in the group, but we have taken conscious step to bring in progressive hypothesis of higher order of complexity. So she asked the right question, did you include energetics? Yeah, we are including now. The competition is so intense that I cannot disclose, not suspecting this audience will leak it to my MIT competitors, but we are working on those models where it is energy informed. Second thing is that can we make this model mechanistically aware? So right now this is like unreacted substrate, catalyst in its native state. There is no active catalyst, no intermediates in the model building, but we have a model. Given the reactant, it will predict intermediate 1, intermediate 2, intermediate 3 and the product. So that is a reaction mechanism model. We call it deep mech. So deep mech is going to be integrated into our the reaction exploration space. These are steps taken one at a time because we don't want to, students' persistence these days, you would perhaps be aware of it. They want the outcome which is quite predictable and it should result in a paper. So they put forward the condition first before starting the project. So I have constraints to answer. So the second part, this was on the
representation of data.
So representation, again, it's a good, interesting territory to work with. So people are moving into what is known as a multimodal learning approach, where you make your representation as a trivial problem. You encode them, but let the model pick what representation works well for the given reaction. So we are not biased towards smiles, or we are a little bit against the use of physical organic descriptors because it involves a pipeline of quantum mechanical computation, which would be slow, although it can be scripted and automated to about 90%. But there are certain descriptors such as vibrational frequency. You require human intervention to certify that this is actually the stretch for that bond. So that would slow down the entire pipeline. When you deal with, say, 1 million reaction, you cannot afford to do vibrational frequency calculation. So otherwise, all modalities are good. But did we see a major difference between different representation and model performance? Answer is no.
Yeah, Professor Sunoj, I really enjoyed your lecture. In the beginning, you just mentioned about the non-covalent interactions. There are several non-covalent. So how do you integrate those non-covalent interaction into your learning sets or so?
So this is a very big, ambitious project with 6 students. There is almost a football team working behind doors on how to incorporate non-covalent interaction to AI space. We are actively on it. So the glimpse of it is like this. We developed pristine dataset for this purpose because the so-called datasets available in literature is almost GIGO. Almost GIGO. What they claim as NCI is not really NCI. There are constrained geometries and so on. There are numerous problems in the case. And the transition state dataset out there is almost GIGO. So we are proving step by step that how much GIGO is flourishing the field. So what we are creating pristine data set for training NCI aware models right now. Initial success is good, looking promising, so we would have to expand by incorporating all these NCIs into our model building. Yeah, it is being done. So the least I can say is that given a binary complex or given a complex structure, it will identify how many NCI contacts are present, how many covalent bonds are present. That's just the starting point. And then it will be able to do more refined analysis.
Thank you.
Students.
Professor Sunoj, just one question. So, is it possible to predict outcomes of this reaction, which you have already talked about some of these, whether they can lead to some innovative products by different mechanisms?
Yeah.
Means, is it what's your experience that you are working on a problem and outcomes are known, but when you applied your tools to study it and the reaction mechanism, you are working on it and it has diverted you to some new avenues?
Yeah. So good question. We have DeepMech as our new model, which is predicting intermediates, which can predict side products, byproducts, and which can intuitively and sometimes counterintuitively refine the yield prediction models, because if there is a background reaction which are not spotted by the primary model, this subsidiary model can alert the main model that there are background reactions. So part of your reactants will be consumed in following the path which you don't want to look at. So yeah, so you would be able to identify unintended products through our model. Yeah.
Great talk, Professor Sunoj. So initially your example was related to total synthesis. So my question is related to when we go for asymmetric synthesis. So change of a single functional group changes the whole result. So when you go for asymmetric hydrogenations, let's say in a total synthesis scenario, so if your groups are changed, so it will change the whole induction, asymmetric induction. So how much effective is your model to predict in those cases?
Yeah. So where is the site of reaction? It is at the double bond, right? And the generalized representation of all those R groups around it is going to impact, but end of the day it is H2 addition across the double bond. And that was my first hypothesis, that the functional group of interest where you are hydrogenating is well taken care by molecular descriptors. So it should in principle work, but maybe it would have higher errors than a well-behaved compound. So if you have so much decorations around the so-called congested double bond, if double bond is already congested, reaction may not happen, right? But if reaction is happening, it should come in about reasonable limits of the ground truth that you would eventually get. It wouldn't be too difficult, but possible.
Okay. Thank you all and thank you, Professor Sunoj, for this useful discussion. This showcases how all of us got connected with your lecture and no one took a nap. So thank you. So now I will request all the dignitaries to join the dais, please. So if you have any questions, we have a interactive session for both student and scientists at 2:30 in hall 2. So please join there. So I request the director to felicitate the speaker with a citation and memento. I request the committee members, Dr. J.R. Gain, Dr. Neeti Kumar for a group photograph, and Dr. P.P. Yadav, please. And me as myself. I now hand over